All right, here we go. What transformations change the graph of f of x to the graph of g of x if f of x is x cubed and g of x is x plus 4 all cubed minus 1? So this is sort of the opposite of what we were doing before. Before I asked you to come up with the equation based on the transformations. Now I'm asking you to compare the two equations and tell me what the transformations must have been. Claudia, what do you think?
You have to add 4 to x, and so it goes 4 to the left.
Okay, so it was translated 4 to the left.
And then y is translated 1 down.
And down 1. There's no stretches or compressions. There's no reflections in there. It's just the two translations. Are we okay with number 5?
Yes, that one seems easy.
All right, so when you flip the page, you're going to see like a summary. This is just a summary of all the transformations. I find that reading them first is not super helpful. It's more helpful to like do a problem and then go back and see if your answer makes sense when you compare it to what's written there. If you just read that, it's just kind of going to make your eyes glaze over. But it's really just a summary of everything that we've talked about so far. There's nothing new in there, so I'm going to skip over it for right now, and we're going to focus on getting all the way through the note sheet. Okay? All right. Number 6, write the function whose graph is the graph of y equals x cubed, but is A, shifted to the right 4 units. Okay, actually, let's try this. I want you guys each to try the A through F. I can't freeze the screen. It's not going to work properly, so I'm just going to do them. So just don't look up until you're ready. Everybody good? All right, so try A through F. All right, questions? E and F. So if we vertically stretch, remember vertical stretches happen to outputs, right? So x cubed is an output. So if I multiply 4 by x cubed, I'm multiplying all the y values by 4. So that's going to stretch that thing up. It's going to look like somebody grabbed the ends and pulled up and down. When I horizontally stretch, remember everything that happens in the horizontal direction is backwards of the way it seems like it should be. So we talked about how numbers bigger than 1 actually compress in the horizontal direction, and numbers smaller, like between 0 and 1, will actually stretch. And when we're talking about stretching on the horizontal axis, it's like somebody grabbed the sides and pulled sideways. So it pulls things away from the y-axis. Whereas compression is pushing things towards the y-axis. Does that make sense? Yes? Okay. It's very awkward with the way the horizontal compressions and stretches are sometimes worded. But when you look at this and they say stretch and 4, the number 4 won't stretch something horizontally. It will compress it. Does that make sense to everybody? Yeah? So it's literally not possible to be a stretch if I stick a 4 in there. In order to stretch it, I have to stick something between 0 and 1 in there. So the like related number would be 1/4, the reciprocal, right? It would be like dividing by 4 instead of multiplying by 4. Is everybody cool with why it's a 4th? But the really big reveal here is that it doesn't end up looking like a 4th because you have to do it to the x before the function is applied. It has to be in parentheses. Well, if I put a 4 in parentheses like that, but then I'm cubing it, 4 times 4 times 4 is 64. So when you simplify the expression, it becomes 1/64 x cubed, which actually means it would look a very same thing as a vertical compression by 1/64. Is everybody okay with that? Yes? Will?
It just was the reflecting thing.
Yep.
So they ended up being the same because there isn't like any cost.
So because this function is something called an odd function, which you're going to be studying on Monday, but your short answer, like short way of thinking about it, is going to be that odd functions have like odd powers instead of even powers. That's not the only definition, but for right now, that's good enough. Okay? So when I have an odd function, if I take a negative number and raise it to an odd power, I get a negative number, right? So whether I take a negative number and raise it to an odd power, or I raise a positive number to the odd power and then take the opposite of that answer, it's the same effect, okay? If I had an even power, it would not turn out the same. right? Because if I have a parabola, it looks the same on the left and the right. So if I reflect that across the y-axis, right, I put in a negative for x before I square it, you can't tell which side I'm on, right? It looks the same on both sides. So an even power there, C and D wouldn't end up with the same equation. Okay, but with an odd power there, C and D will end up with the same equation. Okay? All right, let's look at number 7. Number 7 talks to us about the importance of order, and it helps us to see that order matters when we're applying transformations, so we can't just do it in whatever order we want to. We have to follow a particular pattern. So it says, find the function that is finally graphed after each of the following transformations is applied to the graph of y equals x squared in the order stated, and then graph each on the grid. So we're going to use that like rough draft way of thinking that we did in a previous problem. So if I start with y equals x squared, right? And then I shift it up 2 units. It's just going to look like the same thing but up a little higher. Does that make sense to everybody? Yes or no?
Yes.
Yes. Okay. Then I'm going to shift it right 3 units. So from where it is, it's going to go 3 units to the right. Are we okay? Yes or no?
Yes.
Yes, we're stacking up the transformations, right? Okay, then from here, it says reflect about the x-axis. Where's it going to go? Down below. Okay, so if I reflect across the x-axis, I'm now going to come down here. Are we okay?
Yes.
All right, and then finally, I'm going to reflect across the y-axis. Where's it going to go? The opposite side of the y-axis. So now I'm going to be over here. So if you think about that, what are the coordinates of that vertex? After all that stuff has happened. Negative, not negative 2, negative 3. Negative 3, negative 2. Are we okay with that? All right, so using what we did before, that same like parent function table that we used earlier on this note sheet, if I'm at negative 3, negative 2, I can go over 1 and down 1, over 2 and down 4. This is basically the parabola that I end up with. Negative 3, negative 2. And just like before, I don't really care about a lot of coordinates. I just need a sense of where it is. All right, I'm going to pick a different color to do the other one so that we can tell them apart. All right, so this one is going to have all the same transformations, but we're going to do them in a different order. So I'm still starting with my parent function. Now, it says reflect it about the y-axis. So imagine spinning that parabola around the y-axis. What happens? Lucas?
Literally nothing.
Literally nothing, right? You can't tell. If I reflected about the y-axis, it looks exactly the same. So nothing happened. Claudia?
Never mind.
Okay. Then we're going to shift up 2 units. That sounds familiar. We've done that before. Yeah? Then it says I'm going to reflect about the x-axis. Is that also nothing? No. You'll be able to tell that I reflected across the x-axis. So when I reflect across the x-axis, I'm going to come down here. Then it says shift right 3 units. So I'm going to be over here. Is that where we ended up before? No. What are the coordinates of my vertex now? 3, negative 2. So now it's over here. It's exactly the same shape, but it's in the 4th quadrant instead of in the 3rd. If you go back and look at that list, you'll see it's the exact same 4 transformations, but when they were applied in a different order, it came out differently on the graph. So order is important when we're applying transformations. Questions? Yes?
Is there going to be a kind of problem like this in any sort of assessment?
Probably not. This is more of a develop a thought question.
And
Okay?
if you're looking at the equations, which like I did, I looked at like.
Now, these problems I didn't used to teach. I added these a few years ago to make sure that we were taking this concept to the level that a pre-calculus class might take it. Because this is a topic that's been removed from honors pre-calc, and we really just cover it here. Because it didn't make sense to cover the same topic for 2 years in a row. So I stole this out of Honors Pre-Calc, okay? So you're going to have a classwork assignment later that you're going to start today and probably finish tomorrow. That is literally taken straight from the pre-calculus textbook. All right, so here's the deal. If 3, 6 is a point on the graph of y equals f of x, okay, they're not even telling us what function f of x really is. They're just saying there's some function called f of x, and one of the points on the graph is the point 3, 6, okay? And we don't need to know what the actual function is. We just need to know this one point. It says, which of the following points must be on the graph of y equals f of negative x? Okay, so think about that. F of negative x is what transformation? Lucas?
Isn't that the transformation where like just the x changes?
Just the x changes, so we're reflecting across the y-axis, okay? So you just imagine taking that point, reflecting across the y-axis, where would it be?
It would be b.
It would not be b. Where would it be? I take the point 3, 6, I reflect it across the y-axis, where is it now? Negative 3, 6. We okay?
Yes.
So the key to answering a question like this is thinking about what transformation that is. When you're changing the sign on the input only, that's a reflection across y. Right? That's a reflection across the y-axis. So only the x value will change, and it will only change in sign. Nothing else will change about it. Let's look at number 9, similar type of question. If I have the point 1, 3, it's on the graph of some random function called f of x. Which of the following points must be on the graph of y equals 2 f of x? So first of all, think about what transformation that is. What transformation is that? Vertical stretch. Vertical stretch. So I'm doing a vertical stretch with a factor of 2 to the point 1, 3. What will the point become? Claudia? 1, 6. Right? The x value won't change, but the y value will double because we're doubling the output. All right. Now, instead of just doing one point at a time, you're going to see some problems like this on your classwork activity that you'll do kind of in groups helping each other out. It says the graph of function f is illustrated. So that graph off on the right, that's function f. Use the graph of f as the first step towards graphing each of the functions below. In other words, you always go back to the picture on the right and you base each new problem on that picture on the right. It's not flowing like one problem into the next problem into the next problem, okay? These aren't building up. It says state the type of transformation that is applied. And I will tell you, it's much easier to do the problem if you think about what the transformation is first and then try to do the problem. So capital F of x is equal to f of x plus 3. What transformation is being applied? Claudia? Translate 3 units up. Okay, I'm not going to do it out with you yet. Let's look at B. G of x is f of x plus 2. All right, so in B, g of x, what transformation is being applied? Anna? 2 units left. So we're translating to left. All right, and then C, h of x is f of 2x. What's happening? What transformation? Lucas?
This would be horizontal compression.
Yeah, horizontal compression. So basically, we're taking half of each x value. Is everybody okay with that? Right? Remember we said anything bigger than 1 in the horizontal direction is a compression. So we're not really multiplying by 2, we're really dividing by 2. So we're dividing all of our x values by 2. In other words, we're taking half of all of our x values. All right, I'm going to do them. You're not going to look at me doing them. You're going to try them. You're going to try to make each graph, and then you're going to check your work against my work, okay? And if you're feeling really confused, you're welcome to watch.
So I should finish that sheet.
All right, so whenever you're ready to compare your graphs to mine, when I did my graphs, I just looked at each of the points on the original graph and then moved them according to what the transformation said. But down below, depending on how people think, there are certain things that might click better with them than others. So the other option is to use matrices and do your transformations on the matrices. So if you use -4, if you do a coordinate matrix and then a vector matrix, you can add them together and it'll give you your resulting coordinates. So if you added like those two matrices together underneath the first graph, you would actually get the coordinates that I used to graph the graph. The last one is a little bit weird. We haven't had this side discussion yet. We'll do it tomorrow. But there's a handy dandy little scaling matrix you can use. I'm not going to try to explain that now. I'll explain it tomorrow because we just don't have time today. But that'll be one of the conversations for tomorrow. Okay.